Okay, so this is the next hands-on alpaka setup. And for this, what we will do is edit heat equation.cpp, our first CPP file. Let's go. Oops. Okay, so here we are. We start with a bunch of includes. This is setting up boundaries. You haven't seen it, you won't see it. I'm doing it for you, don't worry. Initialize buffer kernel. This was the first thing that everyone in this room wrote. You filled the initial buffer with the analytical solution. This is the stencil kernel. This is what we wrote just prior to this session, the 5-point stencil. The analytical solution holds the analytical solution. Write image writes out the images you saw. Pretty stuff. This is how you include alpaka in your CPP file. It is super easy. Just include alpaka.hpp and you are done. Over here, we are including another alpaka file. I will explain this in a moment. And I have some standard includes. So what is happening? How do we even start? So first off, let's define some convenience function, convenient defines. So these are used in many places inside alpaka, as Rene already mentioned. The dimension, for example, if I have 2D buffers, I have 2D accelerators, I need this dimensionality everywhere. So first off, I will define the dim. So again, this is literally the first line in the cheat sheet. Maybe not literally the first line, fifth line, but close to the top you will see using dim is dim int and the size of your dimensionality. So our 2D heat equation, spoiler, it's in the name, is two-dimensional. So I define the dim as alpaka dim int and then 2. So this is just to have a convenient definition for later. Next, I will define the index type. So this is the type of, already we were struggling with this in the past, in the previous session. So index type defines the type of the indexes you get, for example, when you say get index, or the type you get when you say get extents. This is also used in many places in alpaka, so it's useful to have a shorthand for this. So usually we use 32-bit types because if you use 64-bit types, you get an overhead. So for example, uint32t is what we were using. So some boilerplate aside. Next, we need to define the ACC. So the accelerator is, what we have been doing is we have been setting the accelerator using CMake, CCMake, and then you go and you choose the accelerators from a list and you say, okay, choose the sequential one, choose the hip backend. And what it is doing is it is setting the activated backends, and we are running the code for all activated alpaka accelerators. And this is what this additional include is doing. It is going over activated accelerator tags and then defining the accelerator using that. This is just because it's easy to run multiple accelerators this way, and for the examples it is useful. But in general, how to do it is in the cheat sheet, defining accelerator type. Okay, I will copy this. ACC GPU hip RT is what we need. GPU hip RT. Yes, of course, using the alpaka namespace. And this requires dim and IDX. And this is how you say in your code that, okay, I want to use the hip accelerator. This is the only place in the code you need to change if you decide tomorrow that I want to run my code on CUDA. Simply just change this to ACC GPU CUDA RT and you are done, something like this.
Immediate. Rather than Cuba.
Uh-huh. So the point is, this is the only place you need to change if you want to switch accelerators. This is where you can see how portable Alpaca can really be. So I will go back to what we were using. So what if you are on a device, you're using a system which has 4 GPUs connected to it? I mean, how do you tell it what GPU you want to run the code on and things like this? So there's a few things that you need to set up. Initially, you need to define the platform, and that is done simply by using alpaka platform CPU. So this is simply defining the host platform. So I will call it that. Host platform. Similarly, I can define the accelerator platform. So, and that is alpaka platform. ACC. As Mehmet already mentioned a few times, the accelerator is just a type on the host. Yes, Brian.
So essentially the difference is that the accelerator describes in principle the class of hardware, and platform specifies the specific physical thing I'm trying to run on.
Oh. Yes and no. The accelerator is more than
Accelerator.
yes, the type accelerator is basically the way you are parallelizing. I wouldn't call it a class of elements. But okay. But roughly yes.
In principle, at this point, you need to define the platform. Wait. It is if you like to have CUDA or yeah, there is a platform. You have also a platform definition. You can really say, oh, I like to have the CUDA platform, but since we know how we like to map later on our indices, we can directly say, okay, if we search the right platform, if we later on use this mapping for the indices, the ACC is defined as the CUDA RT, for example, and it will then select automatically the correct platform, because each index mapping, what is the accelerator, and with all the hardware specifics and so on, has only one platform solution at the end. So we do a little bit code reduction, because normally you would write 2 more lines at this point to figure out the correct type you need to add there.
So once you have the platform, which is much more like the class of accelerating devices, you can say. You can select specific devices. So I would say that, okay, my host device is something I can get from my CPU platform. So this would be alpaka get device by index IDX. So again, this is boilerplate code which you can find on the cheat sheet. Everyone, if you are using alpaka for the first time, please use the cheat sheet. It's amazing. Get device by index. I am literally writing stuff from the cheat sheet. So host platform. So I say, okay, my CPU device, my host device is coming from my host platform. And I need to tell it, maybe I have multiple CPUs. Weird, but maybe. I can say, okay, I want my 0th device. Similarly, we need to do this for the accelerator. So in our case, our GPUs. And
But ACC platform line we have braces upgrade,
thank you.
or
Thank you. And this is how we select the first GPU. So I say get device by index from the ACC platform. So if, for example, when you were asking Lumi to give you one GPU in your VS Code configuration, or however, if you ask for do srun, ask for an interactive job, whatever, if you have multiple GPUs assigned to your job, you will be able to access them individually and say stuff like, oh, this is my device 1 and another would be a device 2. And then you can handle them individually as well. This is why Alpaca is an on-node parallelism solution. Inside the node, you have access to everything, and whatever you want to parallelize inside the node, you do it in Alpaca. Your host, your accelerator, and this is, I now have most of my initial boilerplate. Next, after this, we define our simulation. I will go over this really quickly. I define the size of my simulation. So 64 by 64 is the number of nodes. This is basically the size of my core. Let me. So the size of the green area is the node size. I encourage you to later play with this. So try increasing the size greatly, make it extremely huge, something like this. Play around with it. I encourage it. Next is the halo size. For now, we set the halo size to 1,1. 1,1 is just telling us that, okay, we have one cell in X and one cell in Y as the halo. This is a choice. We could have also defined it as 2 if we wanted to include the right and bottom boundaries, but for now, I'm doing this manually. This is up to you, how you want to define it. For our convenience, we have defined it as 1,1. So sometimes you need to add the halo size twice. This is something you need to be careful about. For example, in the exactly next line, to get the full extent, I say it's number of nodes plus halo size twice. So this gives you the whole size of the domain. We call this the extent. Extent nodes, halo size. The number of time steps in your simulation, the final time in seconds. Then we define dx, dy, so this is 1 meter, and then you divide by the number of nodes you have. You figure out dt in seconds. There's a stability condition, all things you don't have to worry about. but it's just there because in case you play around with the nodes, you might get a simulation which is not converging or just blowing up drastically. So it's important to check the stability for the solver. So with this, we have the alpaka boilerplate sorted. I will quickly show you this slide again. Mehmet showed it a while ago. It's the full heat equation solution. And what we have already done is selected the accelerator type. We have the host device, the accelerator device. We still need to create a queue. I will get to this. What we now need to do is allocate some buffers. So these are the buffers which will hold all my data. Then fill the buffer, then execute the kernel, and then copy stuff around. Basically this. So now I will fill the buffer. First define the buffer that will hold the data. Now, a thing we need to be careful about is you cannot use the same buffer on both the host and the accelerator. Think of it as, because it might most probably is two different physical devices. This is very easy to think about, that you allocate a bunch of memory on the host if you need it, and a bunch of memory on the device. So I will define two different buffers. This is done by, let's look at our cheat sheet. Very easily by saying alloc buff. Auto host buffer is that is all you need to do. So my buffer will have doubles in it, and the index type is IDX. Now, what else do I need to say? I need to tell it the size of my buffer. So I will pass it my extent. And also I need to tell it, oh, okay, what am I creating this buffer for? Is it for my host or for my device, for my GPU? And this is a host buffer, so I will say it's for the host device. Is that how I called it? Check device host. So eventually, when we have solved everything, this is where we will copy all of our solutions to. More importantly, for now, we need to define the device buffers. And as Mehmet explained, when we were looking at this, we use a two buffer solution. So we actually need two buffers on device, one that will hold the current solution and one which will hold the next solution. So we just call them buff current and buff next.
Devices will be different. Devices will be different. Both of them is using their host.
Oh, yes, sorry, I just copied it. I will get to it. So, so this is the device. This is the actual physical device. In case you had multiple GPUs connected, for example, you could have chosen which device you want to give it to. Ah.
Like this device and accelerate.
It is correct, and the definition of
Yes, the naming is what he was pointing out to. Yes, for now we stick to this, but a change in naming is also completely reasonable. Okay, I will use the comments. There we have it. So now we have the buffers. What's next? We need to initialize the buffer. Thankfully, we have already written the stencil, the kernel for it, where you set the buffer to the analytical solution at time 0. So the question is, how do you use it? You know that you wrote it over here in initialize buffer kernel. You see this code. We've done this already. This is inside a struct, which defines a function call operator. So it's a functor. What we need to do is, sorry about the scrolling, yes. First of all, we need to construct an instance of this functor. So I will say initialize buffer kernel init buff kernel. So this is creating an object of my functor. What next? I need to create the work division, which I will pass to this kernel. So if you remember, I'm not sure if you do, but to initialize, what we did is we went over the whole green domain, also the boundaries, so really the full extents. So what we need to do now is create a work division for the full extent of our problem. And we will do this using getValidWorkDiv. So again, referencing the cheat sheet, getValidWorkDiv. So alpaka. So what does getValidWorkDiv need? It says it needs a kernel config. Okay, that's something. What else does it need? It needs the device. Okay, that's the dev.acc. I will get to the kernel config in a second. What else does it need? It needs to know what kernel you're writing the work division for. So this is init buff kernel. It asks for what kernel you are using because in the background, getValidWorkDiv is a very smart and also correspondingly heavy operation to do. It checks if your kernel can actually be run using the workdiv it generates. It checks, for example, how much memory your kernel might be using, and if you can run, if there's enough memory to run all the threads in a block, or if there's some other limitations that you might face. So getValidWorkDiv is something you should not call frequently. You should not have it in a hot loop. This is something that ideally you do once and store it. The alternative is, of course, to define the workdiv manually, which we will also get to later. And what else do you need to pass? You need to pass all the arguments that you give to the init buffer kernel. We can check what those are. The ACC, buff data, pitch, dx, and dy. As I already told you, the ACC is always passed automatically when you execute the kernel, so this is not something you need to worry about. For now, we need to pass the buffer, pitch, dx, and dy. Okay, we can do this. Very easy. I say buffer. Which buffer? Current buffer. Pitch. Interesting. How do we get the pitch? I will tell you soon. Dx and dy, these are things we have already defined very well. So this will give me a valid work division. Okay, Let's fill in the missing blanks. The kernel config. This is the big one. So the kernel config is the place where you define how many blocks you want, how many elements the thread will have, or how many threads you want in a block. This is where you can really configure what you would like to see. So, kernel config is equal to, this is how you do it. Alpaka. Sorry about this. And now I can say, I want the kernel over all of my whole domain. So what I want is to go over the whole extent. So I say, okay, my kernel config should be over the whole extent. And then I tell it that I want how many elements I want per thread. So I will just say alpaka. So this is elements per thread. Sorry, I misspoke earlier. This is really not the place where you define how many threads you need in a block. This is automatically defined by getValidWorkDiv. When we come to manual workdivs, that is where we will define our own number of threads per block. Sorry about my error. So all you need to define is your total extent and the number of elements each thread will process. The number of elements each thread will process is nothing else than alpaka vector. So we define alpaka vec. Simply one element per thread. We usually stick to one element per thread. In case you want to deal with multiple elements for every thread, you can increase this, but you need to be mindful that if you deal with multiple elements for each thread, you need to do this yourself inside the kernel. Later on, so for example, if you initialize, in the initialize buffer kernel, if you were to say, oh, I will initialize 2 elements for every thread, you would need to get the element pointer, not only for this index, but also for the next index, and fill it in inside the kernel. So really something like this, and copy the whole thing, and then add 1, 1 over here to get the next index. Oh, sorry, 0, 1. And this is the whole point of handling multiple elements in the thread yourself. Very well. This should give us the work division, except that we are still missing the pitch. So can someone go through the cheat sheet and tell me how we get the pitch? Yes, please. Ooh, exciting. Kernel config.
Someone is lying.
So
Is it about kernel config?
yes, so the question was the kernel config. We said we have written it with only 2 Arguments, these are the first two arguments, the global thread extent and the elements per thread. What we have not written is the next two, and these are optional arguments which are then set to the default. We can check what if my shortcuts do not work. No. Can someone please check what the optional arguments are? In the meantime, I will proceed.
Could you do a right click and go to solve?
Yes. Go to symbol and no.
F12.
F12 is not working.
It's a
Block
browser.
thread must divide grid thread extent. The third variable is block thread extent must divide grid thread extent, and this is a guide while producing the valid vector. Block thread extent must divide the grid thread extent, so that the produced vector will have a block thread extent which can divide the grid thread extent, and this is by default true. And second one is grid block extent subdivision restriction. If this is unrestricted, the default value is unrestricted, then we don't have any restriction on the block size. But if grid block extent could be, we can, for example, if we don't have any restriction, we have 10 blocks at a single row. This could be a grid, but if grid block extent is not unrestricted, for example, if it is balanced, then instead of one row with 10, we are most probably going to have 4 by 4 blocks in a grid, because it needs to be balanced. The sizes would be balanced.
I think that's
Yeah. Okay.
So the other arguments of kernel config are just, as Mehmet explained, advanced guides to get better work divs that are more suitable. At all, the getValidWorkDiv function is a convenience function which you can use to avoid defining manual work divisions. So this is like a smart function, and you can give it hints about what kind of work division you would like. So I have defined my work division. I was waiting for someone to tell me how to get the pitch. Oh, get pitch in bytes. Right, very nice. Someone will hog all the sweets tomorrow. You can see it.
Is it going to be a pointer or a vector?
So the question is, alpaka get pitches in bytes. What does it return? The answer is it returns an alpaka vector holding the pitches in bytes for each dimension. Yes, we name things wonderfully.
It pitches in bytes to go to the next element in the corresponding dimension.
So I want this for my current buffer. And I will say auto cur pitch. So there you have it. This should define a valid work division. Okay. Extent work division. I will call it the extent work division because it is going over the full extent. Later on, when we want to go over only the core, we will define another work division, which is only going over the core section. So now I have a work division, I have a kernel object. What's next? I want to execute this kernel. So this is done using alpaka exec. Yes. And let's see what alpaka exec needs from us. So it is asking for the ACC, of course. The first thing it wants is the queue. So as Mehmet already explained the concept of a queue, it's like a stream in CUDA. It can be blocking or non-blocking. It's where you submit your jobs to. So for a non-blocking queue, which is what we will create, the alpaka exec command will create the task and send the task to the GPU, and you will get control back, and your code will continue to run. Your job will be queued in this queue, and we continue. So it asks for a queue. We haven't made one yet, so we will. What else does it need? It needs the work division, which we already have. Cool. It needs the kernel, okay, the kernel object. And then it needs, since this is how you execute the kernel, it needs everything you are going to pass to the kernel. So these are the parameters init buffer kernel takes. The buffer, the pitches, dx and dy. And this is how you execute your kernel. What is left, of course, is to just define our queue. It is very simple. Just an alpaka queue. Needs the ACC, and it also needs a type which tells you if it's a blocking queue or a non-blocking queue. We will say it is non-blocking. And finally, you tell it which device you want the queue for. And that is pretty much it. Oh, I already have the stuff. But at least you know how to do it now. So alpaka queue, give it, it's non-blocking, you define the ACC, this creates the queue.
Converting buffered pointer by that data.
So Mehmet has found a bug in the code I wrote. So currently what I'm doing is I'm passing the buffer directly into the kernel. And this is a mistake which is very easy to make. Hey, I have a buffer. My buffer is the memory, right? And I just pass this memory to my kernel and it will do stuff with it. But actually, you cannot pass the alpaka buffer object directly to the kernel. What you pass is, can someone tell me what do you pass to the kernel? A memory pointer, perfect. So the way to do this is by saying .data. You can also use standard data if you want. The alpaka buffer is much like standard containers. So yes. This gives you the pointer of the memory which the buffer holds.
Maybe we also have DT in the channel.
No.
This is info from.
Okay. I will move this to the correct location. Move this to the correct location. Okay. Questions, pain points. None. So let's continue. What do we have till now? We have created the buffer we need. We have initialized the buffer on device. Mind you, we have done nothing with the buffer on host. It still contains garbage, probably. So what's next? After initialization, we need to start our main simulation. We wrote the stencil kernel already. So we need to run it. Obviously, you can see I have the for loop and I can start writing inside, but just to think about it, you don't want to create the kernel object inside a hot loop. You call the same stencil over and over again at every iteration. So what we can do is create the kernel object outside. So executing the main simulation. So I need a stencil kernel. I will look at it. Called stencil kernel. Very nice. Similarly to the last step, I created the kernel object. What's next? I create a kernel, a work division. I will copy and paste it. Elements per thread is already defined. I could have used the same work division, almost. It's not recommended because first, it's a valid work division only for the init buffer kernel. So your new kernel might have different properties, might be using more memory, this work division might not be valid for your new kernel. So it's important if you're using get valid work div, and if you're not sure if your kernel and work div match, to do it for every kernel. So we do it. Let's start from the top. We create the kernel config first. So what's different in this kernel configuration? Previously, we were going over the full extent. Now we only want to go over the core portion of our simulation. We don't want to apply the stencil to the boundaries. And you remember we had the offset for the halo. So we only want to go over the core region. And that is given by, if you scroll up, num nodes. Num nodes is the core without the halo. Perfect. Next, we need to get the pitches. So let's get to it in a while. First, let's try to see what get valid work div needs. It needs the config. So let's name this something else. Kernel config core. So because we only go over the core. The device is the same. I need my kernel. Next, I need all the things I'm going to pass to my stencil kernel. Let's look at the kernel again. It needs quite a few things. So it needs two buffers, the current and the next buffer. It needs pitches. Obviously, we pass pointers. We also need pitches. So current and next pitch. It needs the halo size because you want to transform the origin to the correct place. And then it needs dx, dy, and dt. So let's pass everything. Obviously, this is so current buffer, next buffer. Let's see what it's called. Device next buffer, very nice. Current pitches. Now I need next pitches. So I will get them. I will define them here just to keep things tidy. And this is the next pitches. I need dx, dy, dt. What else? Halo size. And this should give me the work dev over the core. Now that I have the kernel object, I have a fitting work division. The next thing to do is just execute it. And obviously I don't want to execute it over here. This is the main simulation code. So I do this inside the for loop. So alpaka exec needs the ACC. The first argument is the queue. Now we created a non-blocking queue. That means as soon as the job is submitted to the device, it returns back to continue execution of the host code. What this means is over here, once this was written, the job to initialize the buffer is sent to the GPU, but you don't know when it starts. Maybe I had some other code which was already running on the GPU and things don't start instantly. There are latencies. You don't know when the job starts and when the job ends. There is no other synchronization. What we use for synchronization is just the queue. So I have added the initialize buffer to this queue, and if I add the stencil kernel to the same queue, it just makes sure that the stencil kernel will not be executed before all the previous tasks in the queue are finished. So the queue is really a synchronization mechanism, and that's how we use it. So we need the queue, we need the work division, and we need our stencil with all the arguments you need to send to it. And I think that's it. Yes. And this will apply the stencil. After that, I have some code which applies boundaries. This is very similar to the code we've written before, so we won't go into it. There is some stuff which is conditionally disabled, which writes out the images. Again, nothing you want to worry about. Finally, since we are using two buffers, I will go back to the image shortly. We are using two buffers, and okay, once you apply the core, you go from U0 to U1. Buffer next is filled with the solution at time step 1. To go to the next step, what you need to do is swap both buffers. And so the current will hold U1 and the next will hold U0, and you can just throw away U0 because you've already used it, you've created what you want with it, and now you can fill it with U2. So with just two buffers, we can do the whole simulation. So what's left is to swap both the buffers, and we can just simply do it using standard swap. And we give it both the buffers. And that should do it. So this looks easy, but there is some thinking involved here. Because what is happening is I am calling alpaka exec. And this is only putting the task into my queue and then returning the flow of control to the host. So, okay, this was called. Apply boundaries was called. I still need to fill in arguments. The image was created if it needed to be created. And then I said I will swap the buffers. But really, what happens if I swap the buffers before my kernel was actually executed? I don't know when my kernel is executed. Maybe it's still enqueued. Maybe I'm still initializing my initial buffer and my core stencil is not running yet. What if I swap before it? Isn't that a problem? It can be. And this is something you need to be careful about. Over here, it is not a problem, and this is correct. Because what you are passing to the alpaka exec is a pointer to the buffer data. And initially, you pass the correct pointers. It will swap the buffers, including the pointers, but not the actual data it is pointing to, if that makes any sense. Is someone confused about this?
You can show from the graph.
Uh-huh. Yes, so swapping really swaps the pointers, and that's all. And the next time you call enqueue, it is enqueuing the task with the opposite pointers, and this way you're always in the queue calling the core over the correct order of the buffer.
Should we switch the pitches as well? The cure pitches and the next pitches?
Yes, we should. This is excellent, and this is actually an oversight on my part that I have completely looked over. But yes, we should swap the pitches as well. Let's do it.
But here can we use STT?
Probably.
But since buffers are the same,
Yes.
layer sizes are the same, pitches are the same, data sizes are the same, I don't think it is necessary.
Yes, and in general, 2 pitches is not necessary for this example at all because our buffers are identical.
Yeah.
But in principle, to be safe, this is what would be needed.
I mean, if we have 2 pitches,
And this is also probably broken because if I do this, I will face the problem I was describing because these are not pointers and these are actual vectors. So,
but it does not do a copy, like
It depends on if you pass by value by reference.
Rather than swapping,
Yeah, so-
we can just assign.
this actually brings us to a good point.
Why you are worried about the swap?
No, so Julian pointed out another point that when we pass an object to a kernel, it is passed by copy because it is being passed to another device, most likely. So again, this is not something you have to worry about. This is why the swap will work.
Why we are just not assigning current pitches to next pitches then? Yeah, I mean, because swap is cheap. If there are pointers and we want to swap just pointers, but we can just assign because we need just to swap 2 elements.
Yeah, swap is just convenient. So this should do it. There is some stuff that needs to be filled in for apply boundaries as well. I will do it in a moment. Not something you need to be worried about. It's basically exactly the same thing. apply boundaries also hides an alpaka exec, and it also hides another kernel, which is applying only the boundary conditions. So what do we have till now? What we have done is everything here, allocated the buffer, filled the buffer with initial conditions, executed the stencil on the grid, executed the border, swapped the pointers. We do this in a loop, and finally, we want to copy the buffer to host. So let's do it. We copy from device to host finally, and guess what it's called? It's just alpaka mem copy. And mem copy is written from source to device. Oh, let me check. From source to destination?
Destination is the last.
Yes.
The second source is the last.
Yes. So, current buffer. And host buffer, yes. So, memcopy from buffer to buffer, really?
You know, we have
Yes, of course.
yeah.
Good catch.
We are copying to the.
Oh no.
Therefore, the second.
So as you can see, I make a lot of errors, and please refer to the cheat sheet. It's amazing. So really, for the mem copy, the correct way to do it is say the queue, and then the destination, and then finally the source.
It follows the standard mem copy.
It follows the interface of the standard mem copy. Destination, host. Okay. And after this, we have some validation code to check if everything is fine. I will give people a few moments to let this all sink in while I fill the apply boundaries.
Could it be that you never wait for your result?
Good catch. So I am quite happy with my audience today. So I put my alpaka mem copy in a queue. So everything is in the queue. My simulation runs, but while it's running, I never wait for it to finish. I'm doing the validation, but the validation is done on the host after I copy it to the host. And I never waited for my things to actually execute because my queue was non-blocking.
It is not after you copied it, after you said that you like to copy.
Exactly. The comment was that I don't execute it after the copy. This is just saying that, oh, I want to do the copy. I just enqueued the task to the queue and just started doing stuff again. So before validating, I want to make sure that this copy is actually done, that the queue is actually empty. And for this, we wait. Alpaka, wait. Simply alpaka wait. On our queue. This will do it. So this is where you pause after all the work is done.
Yeah, short few words during everyone is waiting. As already said, the queues are, even if you set it blocking, this means only that from the thread or from the process where the API call enqueue wait or something like that is enqueued or create something is enqueued, this thread will be blocked. So it is not getting the handle back until the operation is finished. If you have non-blocking, you will instantly get the handle back. And this means if you define a blocking queue, but you write an application with two threads, which are accessing the same queue, what is allowed? So our objects are thread safe from the CPU side. And both threads enqueuing something into a blocking queue, this does not mean that the second thread is waiting until the first thread has something enqueued, because the order of the thread execution is not defined. They are running in parallel. So only the thread who is enqueuing something, this thread will be blocked until the stuff this thread has enqueued is finished. The second thread is not waiting for anything. So this could very easily misinterpreted, and this does not mean that parallel threads on a CPU accessing the same object, that they are waiting. Therefore, in many cases, the blocking queues are also used very often only for simplification. If you have a single-threaded program, that you can very fast do your operation, your API calls to Alpaka, you do not need to care about synchronization, because you have only one thread and you enqueue everything in one queue. So it is also a little bit something like for debugging purpose. So in principle, even if you talk about HPC, you should always prefer to use a non-blocking queue, because this gives you the possibility to overlap work, even if you have only one thread, but you have a device where you push your work to, and this means you can push two kernels into the same queue or a different queue, and you can go on with host operation to prepare something or whatever. So you really utilize your device much better. So use a blocking queue only for debugging for the first steps, and later on you should use the non-blocking queue, and you should always take care about the synchronization with waits if you access your memory or you need to wait between two queues.
Thank you. So just for completeness, so I fill everything in. When we want to write the image, we also need to, so writing the image is something that is done on the host side. So we need to transfer our current state back to the host, and to do this, we need to do exactly what we did at the end for verification, to copy our current buffer to the host and then wait. Let's think about this.
I'll repeat the question, please.
So the question is, should we copy the current buffer or the next buffer? This is a very good question. So what is happening at step 1? The current buffer holds the initial conditions and the next buffer holds the condition at step 1, solution at step 1. Yeah, my current call is writing the image at 1 before the step, so current buffer is correct. But in other cases, if I was to use the latest information, for example, like this, then I would need to use the next buffer. I do this because
if we do after the swap, then we can always use the current. Because if we do the main copy after the swap, then we can always use the current, which will be the latest.
Yes.
Yeah.
Yes, the idea was not to use the latest always, because this way writing out the initial conditions as an image was easier. It could happen inside the loop. Again, this is a small preference, and this could have been done either way.
An advantage to do it like that is also if you have a second queue, so a little bit more advanced, then you could could already copy the data from the current step where you in your standstill kernel only access it readable. then you could at the same moment copy already the data to the CPU because it's also only a read, and later on wait then until this copy is finished so you can overlap the memory copy operation with the task of the stencil kernel.
So the comment for the people online is that another benefit of doing the mem copy from the current buffer, the buffer which is being read only, is that later on, if you can use two queues, there is the possibility to parallelize the copy from the current buffer on the device to the host alongside the time when the computation is taking place. So this is also something we will cover tomorrow. But this is an excellent point.
It's just, in this case, it's just confusing that it's after the calculation. And there is one image missing.
The last image is missing, yes. So to do it properly, there should be another write image over here afterwards, or as you prefer, if you write out the current image here, then an initial image needs to be created beforehand. This is matter of taste. Yes.
And the apply boundaries should be filled in.
Yes, we should fill it in, and let me do it right now. So apply boundaries is, I can show you shortly. It is nothing but another kernel which is applying boundaries. It checks if you are actually on the boundary, and if you are on the boundary, it sets your boundary to the analytical solution at position and dt timestamp. And the apply boundaries function is just calling your boundary kernel and calling alpaka exec. So it's just a helper, and to hide away all of this, it was written. So it takes the work division, takes the queue, and then the arguments to the kernel, and I will fill it in. So extent work division, queue. I just realized that the interface isn't quite consistent. The queue usually comes before the work division. Sorry about that. What else do we need? So this needs the buffer, pitch, timestep, dx, dy, dt. So this is buffer, pitch, step, dx, dy, and dt. Okay. And yes, that should be it. Don't worry if you were not able to follow all of this. What is most important is that you understand the concepts going on behind this. At the end of the day, this is a lot of knowing the API of Alpaca, a bunch of boilerplate that you need to know, the concepts of creating buffers, of how queues work, of how you can execute something, of how you can create a work division. These are important to understand. And I hope you do. So let's try compiling. Yes, a risky thing to do, especially live. I will only enable the HIP compiler to speed things up. Okay. Use of undefined ubuff host, of course. No member named get device by index. Oh, so even looking at the cheat sheet, I still make mistakes. Shorter names, nicer. What else? Undefined u buff host, expected a semicolon. C++, C++. It's important to end your statements. Yes. Okay. And what is the host buffer called? It is called host buff. Let's try again. Redefinition of current pitches. Oh no.
Yeah, there's a comment in the chat, current pitch must be next pitches. Or current pitches.
Where? Yes, 136 redefinition.
You defined it.
Yes, I have defined it before. Yes, sorry about that.
Oh no, was it not that you need to rename this to next pitches? Or
No, I really had a redefinition, a copy paste error.
Yeah, you moved it up.
Yes. So next pitches is over here. And something really ugly. So we scroll up to the top. Make current pitches, redefinition, already did this. Okay, invalid operands to a binary expression. I made the same mistake. This is in stencil kernel. Right. Sorry about this. I will fix.
Just change.
You can also simply add u at all the numbers. It's also fine.
They're negative.
Minus one u is fine.
Just
Yes.
remove.
But someone mentioned this C++ 20 fine. That's fine.
Is LM defined? Or is LM defined?
No, it isn't.
Or
Okay, that works. And now to run it. Thankfully, execution results are correct. So, yes, a little bit of debugging, a little bit of small errors, but I hope the concepts are clear. The most important is, of course, defining the work division. In my opinion, this is the most complex portion. Yes, Richard.
The question regarding
Yes.
So you have this core word division, which takes exactly the same arguments as your execution. Why this duplication?
So get valid work div again is a really smart helper, and it analyzes your kernel. So it requires all the arguments that your kernel will take. Exec executes your kernel and also takes all the arguments that your kernel will take. But you are absolutely right that this is a duplication. And to reduce this, I think we have something called a kernel bundle. No, we don't. Sorry,
It's done.
it's gone.
Yeah,
Old news.
to remove this redundancy, I implemented the kernel bundle, but
It's a thing of the past. So
Yeah, it created a kind of performance problems because it necessitates additional copies. Therefore, we haven't used it, but I'm still thinking about a solution. Most probably, we will find
yes,
one.
but
And the tuple, STD tuple, we couldn't use the STD tuple.
so the problem with using a standard tuple is that the standard tuple is not a trivially copyable type. So yes, Rene?
Yeah, so in principle, yes, this is a duplication of that you need to write the parameters, and you can easily make a mistake that you pass in the get valid directive maybe another parameters, and then in the kernel you use also other, and then in principle it can be that the work division is not fitting anymore, because really the work division has some requirements, how much registers your memory your kernel requires, and this defines the limitation we take into account in this get valid directive, and this could be violated if you use different parameters. And in any case, if we use some helper constructs, for example, to bind together the kernel with other arguments, we always have an additional copy of the arguments. So you need, if you call a kernel, each argument and also the kernel must be trivially copyable. This is a requirement alpaka is defining, because this is defined by CUDA, for example, because you go to another memory hierarchy, you go to another device. This really means data must be copied. It does not mean only the copy operator should be called, because the copy operator is not required to be a copy. You really need to copy byte or bitwise the values to another device. And in case we would bind something together, like all arguments into a tuple or something, we will have an additional copy on the device, and this could be very expensive. If we now only pass the data here as arguments, and for the validation we do not really need the data, we need all the data signatures, because a kernel is nothing else than, you could think of a function signature in C++ for the host function, and we need the full signatures with all templates and everything to then query the limitations for this signature. And if we would bundle it somehow, we would do a copy of this of the objects. And if you we observed performance penalties if you have 100 arguments, for example, or 1,000. We did several tests, and then you really realize an overhead. And it depends really on what the arguments are. So if it is only some integers, maybe it is not so obvious, and if you have 2 or 3, but if you have large complex objects which are maybe 100 of megabyte or so, then it could be really a problem. Okay, I don't think that you can pass an object with 100 megabytes to a GPU kernel as parameter, but this was now more theoretical example. And that's the reason why we stick currently still to the interface with the duplication. So it's a performance decision.
I mean, if it's just performance, we could have 2 signatures. One for then people.
But then the user is complaining about performance.
Yeah, will not think, oh, actually I should duplicate. don't know.
Yes. So how is everybody doing? It's 13 minutes to the end of the first day. We haven't covered all the material I planned for today yet, but it's not a problem. We can move it to tomorrow, speed it up a little bit. Is everyone following? Yes? Oh, awesome. So just to really hammer it home and make sure you understand what is happening, I'll go over the whole code again, just describing what happened. So first, we defined our platform, our device, our ACC. Really, these are the actual devices. This is the acceleration scheme. So this will be alpaka, ACC, GPU, HIP, something like this, mentioned in the cheat sheet. Please refer to it. After that, we define our simulation parameters, the size of the simulation in nodes, the halo size, the extent, time steps, dx, dy, stuff like this. We allocate memory, simply alloc buff, allocate memory on host, allocate memory on the accelerator. We create the initialization buffer, we create the work division for it, we create a queue, and we enqueue the execution of the initialization. Very nice. After that, we create the stencil kernel, which is our main computational kernel. We create a work division for this computational kernel, which is different because it only goes over the core. And then we execute, or we enqueue the execution. We apply boundary conditions, we write the image, we swap, and we do this for our whole simulation. At the end of the for loop, which is basically completed almost instantly because it's not actually doing any computation, it's only enqueuing things to the GPU, we finally say, okay, I did all the work, or all the work will be done soon. I want to copy my memory back to host. I say once the copy from host is done, I wait. So this really waits for the whole queue to finish, initialization, all the computation in the for loop, find the final mem copy, and then we validate. And that is our whole alpaka program. Inside the computational kernel, we've already seen. We've seen the init buffer kernel. We've seen how to deal with ugly pointers. And tomorrow, our plan would be to first check out what mdspan does. So you won't have to do the reinterpret casts, and you won't have to deal with pitches and pointers. You can really use the mdspan object on a buffer, and this would simplify your life a whole lot. It also simplifies how you access elements inside a kernel. So it's going to be a quality of life improvement. After that, we will also look at creating work divisions by our own. So for now, we have asked alpaka to create the work division given the full extent of our problem and how many elements we want each thread to calculate. But tomorrow we will really divide our domain into small chunks, which we will pass to individual blocks, and then really define our work division manually. After that, we have a few optimizations, like Rene mentioned, using 2 queues. And finally, if we have time, we will show how shared memory works. Don't worry, these are short steps. Hopefully, will be done soon enough. So with that, I would say let's just look at if people have any more questions. Otherwise, we are done for the day. Yes, so Rene has some comments.
So I think it was mentioned, but I'm not fully sure. So what is the alpaka version we're currently using is the latest release. It is C++ 17 because we throw it in the room sometimes C++ 20. So the minimum requirement for the current version you are using here is C++ 17 or 20. You can use both of them. And what you also have realized maybe, what is very important is that alpaka is written with object-oriented objects at all, but the interface you're using is full functional. So you always say wait and you pass the queue. You not say on a queue, give me a wait. This has some design choices that you can really optimize Alpaca, and all the implementations you can say are some stuff what is working, but you can always change the behavior in Alpaca. So we will not cover this part because this is interesting for you if you like to become an Alpaca developer, or if you really like to change the behavior of Alpaca for some reason. So we have users which change the behavior of a queue. This is possible, therefore also the design decision of having a functional interface. That is something you should know about, because very often we got asked, why can I not say queue.wait, queue.enqueue something, or something like that? Then maybe also the IDE would help you with interfaces that you press dot and you get all the possible functions you can call. This is not the case, therefore also the recommendation to open the cheat sheet and look what functions you can use, for example, to get some properties from the queue or to enqueue, something like that. It's now your stage again. Thanks.
Cool. So, any further questions? Let's look at the chat. Someone says that please don't let it be faster than today. Don't worry, we won't rush through anything. Thank you for the comment.
Yeah. When you do some errors, like the logs, the compilation times are very long, like it's very difficult to find what is the root with all the templates.
Yes, it's true. So the question was, or the comment was that when you make a small error, like I did a lot of times today, the compiler throws huge errors, and even just scrolling through these errors is A, time consuming, and B, slightly intimidating. And it's hard to find sometimes where the actual error is. What I can say is it gets better with time as you get used to it. I mean, the situation is how it is with the templated errors. But as Rene says, switching to C++20 soon will be some changes how templates are used, introduction of concepts, and error messages should get better. Yes, Richard.
Most of the errors are also at the beginning, so typing into less, or for example, for that kind of terminal, typing clear before compiling, and then just scrolling up till it ends helps a lot.
Yes, that's a
Just
great
the
point.
help of your errors.
Also, so the point.
Still before the error in my code, I have before 1, 2, 3, 4 events of templates. So I need to find.
My personal recommendation is always pipe the result of your compiler into a file, and then you use essentially to search for error, the word error. And usually you get essentially it comes from here, comes from here, comes from here, and then here's the actual error.
So some of the recommendations in the room were piping things to less, only checking out the starting of the error log, because if you have to solve errors, you need to start at the top, because as Rene already mentioned, the errors below must be follow-on errors. It's possible. And another recommendation was to pipe all the compiler output to a text file and then Control F, search for an error. And that's also a way to do it. Again, in my personal experience, as you keep using it, you get used to it, you are able to see what is going wrong.
Sometimes changing the accelerator is also a method to find the bugs, because you can easily change the backend, and running with different compiler is also sometimes a good way to understand the error, in my opinion.
Yeah, so this is a good debugging tip in general. Changing your accelerator if something is broken, maybe there's a race condition in your code, you can't understand what is happening, it is very useful to just switch the accelerator to a serial one, see if at least your code works there. If not, then at least you can narrow down where the error is coming from.
Also, can switch between from MPCC or CC to Clang or GC to get much better error messages.
So, like Mehmet already mentioned, Simeon also says that switching from GCC to Clang or vice versa, from HipCC to
There are
GCC.
many variables to change easily the compiler.
Yes, so if you can change the compiler, you might get better error messages.
Even don't get any error if I change compilers.
Yes, so this happens. The comment was that by changing compilers, all the errors disappeared. It happens. And this is why, while developing Alpaka, we have a very extensive, really extensive set of compiler combinations that we test. We test compilers with different versions of Boost, and all sorts of things.
With different versions of compilers.
Yes, with different versions of the same compiler, etc. All right, in that case, I will call the meeting to a close. Thank you everyone online and in person for joining. I hope this really makes you more confident in using Alpaka. I would say this is not very complicated to do in terms of GPU programming. This is the basic of all the concepts, and if you have followed what we had to discuss today, I think you have overcome the biggest hurdle you will ever face. Everything from now on is simpler. If you understand these basics, you can build practically anything on top of this. So thank you, and now we will stop the recording. I will stay in the room for a while just to see if there are any more